Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through 50 cosmic discoveries that change the way human beings understand the universe. For now, imagine the night sky as a quiet archive. Every star is a small point of light, but every point has a history. Some light has traveled for minutes. Some has traveled for years. Some has crossed the universe for billions of years, arriving at Earth long after the place that sent it has changed. A cosmic discovery is not always a sudden answer. Often it is a faint signal noticed in the dark, a wobble in a star, a pulse in a radio dish, a galaxy whose light is shifted toward red, a tiny difference in ancient radiation, a curved arc of light where gravity has bent the path of a more distant galaxy. Tonight's journey moves from the earliest light we can observe to black holes, gravitational waves, alien worlds, icy moons, hidden matter, enormous galaxy structures, and the living frontier of modern astronomy. Some discoveries are settled foundations. Some are still debated. Some are candidates, hints, or open questions. Together, they make the universe feel both more understandable and more mysterious. We begin with old light. Long before stars, planets, or galaxies existed in their familiar form, the universe was hot, dense, and filled with particles and radiation. Light could not travel freely because it kept scattering from charged particles. The young universe was like a glowing fog. Then, after about 380,000 years, the universe cooled enough for atoms to form. Light was released into space, and that ancient light has been traveling ever since. Today, it reaches us as the cosmic microwave background, a faint glow coming from every direction. When Arno Penzias and Robert Wilson detected a persistent microwave hiss in the 1960s, they were not trying to hear the beginning of the universe. They were working with a radio antenna and trying to remove a signal that would not go away. But the signal was real. It matched what cosmologists expected from a hot, early universe. The cosmic microwave background is not a photograph of the first instant. It is more like the earliest page of the universe that light can still show us directly. It tells us that the universe was once far hotter, denser, and smoother than it is now. That discovery sits beside another, the expansion of the universe. In the early 20th century, astronomers began to see that many galaxies were not sitting still in a fixed cosmic stage. Their light was shifted, and the farther away a galaxy was, the faster it generally seemed to be receding. Edwin Hubble's observations helped make this pattern famous, though the story also includes earlier theoretical and observational work by scientists such as Georges Lemaitre and Vesto Slipher. The important idea is gentle and enormous. Space itself can stretch. Distant galaxies are not simply rockets flying through an empty room. On the largest scales, the distance between unbound galaxies can grow because the scale of the universe changes. If the universe is expanding now, then the mind can run the story backward. The galaxies draw closer. The radiation becomes hotter. Matter becomes denser. The universe approaches an earlier hot, compact state. This is the heart of the Big Bang model, not an explosion into space, but the expansion of space from a much hotter beginning. Then, near the end of the 20th century, a second surprise arrived. Astronomers studying distant supernovae found that cosmic expansion was not merely continuing, it appeared to be accelerating. The name given to this mystery is dark energy. It is not a fully understood substance held in a jar. It is a name for the unknown cause, or effective description, of the accelerating expansion. In the standard cosmological model, dark energy makes up most of the universe's total energy budget. This is one of the quietest shocks in science. The universe is not only expanding, its expansion has changed over cosmic history. On the largest scales, the future of the cosmos is shaped by something we can measure by its effects, but do not yet deeply understand. Now the journey turns from the whole universe to the deepest wells in space-time. Black holes began as a mathematical possibility inside general relativity. If enough mass were compressed into a small enough region, space-time could curve so strongly that no future path would lead outward past a boundary called the event horizon. For a long time, black holes felt almost unreal. They were too extreme. They seemed like warnings hidden in equations. Then the sky began to provide evidence. Cygnus X1 became one of the first strong black hole candidates. It is a bright X-ray source in a stellar system where an unseen compact object pulls matter from a companion star. The X-rays come from gas heated violently as it falls inward. The inferred mass was too great for a neutron star, making a black hole the best explanation. A black hole is not a dark, solid ball. It is a region of space-time. Around it, gas can glow, stars can orbit, light can bend, gravity can reveal what the eye cannot see. In 2019, the Event Horizon Telescope gave the world the first image of a black hole's shadow in the galaxy Messier 87. The image showed a ring of glowing material around a central darkness, shaped by gravity, motion, and the path of light near the event horizon. A few years later, the same telescope network imaged Sagittarius A star, the supermassive black hole at the center of the Milky Way. This discovery was closer to home, in our own galaxy, but also harder in a way. Sagittarius. A star changes quickly because it is far smaller than the black hole in Messier 87. Together, these images did not show a surface. They showed the environment around an object whose gravity changes the routes light can take. They turned a century of theory into something visible enough to recognize. Then the universe gave us a new sense. In 2015, LIGO detected gravitational waves from two merging black holes. These waves were ripples in space-time itself, carrying information from a collision more than 1 billion years away. Einstein's theory had predicted gravitational waves a century earlier, but detecting them required instruments sensitive enough to measure changes far smaller than the width of an atom. The discovery did more than confirm a prediction. It opened gravitational wave astronomy. For most of history, astronomy meant light. Visible light, radio waves, X-rays, infrared, and other forms of electromagnetic radiation. Gravitational waves are different. They let us listen to the motion of massive objects directly through space-time. Soon after, another event made the new era even richer. A neutron star merger called GW 170817 was detected in gravitational waves and also seen in light across the electromagnetic spectrum. This was multi-messenger astronomy, one cosmic event arriving through more than one kind of signal. Neutron-star mergers matter because neutron stars are the collapsed cores of massive stars packed with matter at extraordinary density. When two neutron stars collide, they can forge heavy elements such as gold and platinum. The jewelry on Earth, the platinum in instruments, the heavy atoms scattered through matter, all connect back to cosmic violence softened by time. The sky also revealed other compact stars. In 1967, Jocelyn Bell Burnell discovered regular radio pulses coming from space. These pulses were so precise and strange that they first seemed almost impossible. They were eventually understood as pulsars, rapidly rotating neutron stars with beams of radiation sweeping across Earth like lighthouse beams. Some pulsars rotate many times per second. Their timing can be so steady that astronomers use them as cosmic clocks. Across many years, tiny shifts in pulsar arrival times can reveal subtle effects, including evidence for very low-frequency gravitational waves passing through the galaxy. In 2023, pulsar timing arrays, including nanograv, reported strong evidence for a background of nanohertz gravitational waves. The likely source is a population of supermassive black hole binaries throughout the universe, though researchers continue to test the exact origin of the signal. It is not one sharp chirp like LIGO's first detection. It is more like a deep cosmic murmur spread across the sky. The universe also speaks in sudden flashes. Gamma-ray bursts were first detected by satellites watching for nuclear tests during the Cold War. Instead of coming from Earth, the flashes came from space. They are among the most energetic explosions known, associated with the collapse of massive stars or with neutron-star mergers. Fast radio bursts are shorter and more mysterious. These millisecond radio flashes can come from far beyond the Milky Way. Some repeat, some do not. Magnetars, which are highly magnetic neutron stars, are a leading explanation for at least some of them, but the full story is still being written. A single fast radio burst can cross enormous distances before it arrives as a faint signal in a telescope. It lasts less than a blink, yet it may carry information about the thin matter between galaxies. Now let the journey move toward planets. For centuries, people wondered whether other stars had worlds. The first confirmed planet around a sun-like star, 51 Pegasi b, changed that question in 1995. It was not Earth-like. It was a giant planet orbiting close to its star, moving around in only a few days. But its discovery proved that planets could be found around ordinary stars. Then came the Kepler Space Telescope. Kepler stared at a crowded region of sky and watched for tiny dips in starlight, the slight dimming that happens when a planet crosses in front of its star. From those dips, Kepler revealed that planets are common throughout the galaxy. This discovery changed the emotional shape of the night sky. Stars were no longer only stars. Many were suns with worlds around them. Some systems held multiple planets. Some planets were larger than Earth, but smaller than Neptune. Some orbited in regions where liquid water might be possible under the right conditions. The TRAPPIST-1 system gave this idea a vivid form. Around one small, cool star, astronomers found 7 roughly Earth-sized planets. Several orbit in or near the star's habitable zone, where temperatures could allow liquid water if the atmospheres and surface conditions are right. The phrase habitable zone is useful, but it is not a promise. A planet can be in the right orbital region and still be dry, airless, frozen, overheated, or chemically hostile. Habitability depends on atmosphere, water, geology, radiation, magnetic environment, and time. Proxima Centauri b brought the question closer. It orbits the nearest star to the Sun, a little more than 4 light-years away. Even at the speed of light, a message would take more than 4 years to cross that distance. With current spacecraft, the journey would be far longer. The nearest known, potentially temperate world is close by cosmic standards and still astonishingly remote. Some planets do not orbit any star at all. Rogue planets drift freely through the galaxy, perhaps thrown out of young systems by gravitational encounters. A world without a sunrise may sound lonely, but if it carries internal heat, a thick atmosphere, or subsurface oceans, it might still have its own kind of hidden environment. Other discoveries remind us that our own solar system is still full of surprises. Mars carries the marks of ancient water. Orbiters and rovers have found dried river valleys, lake beds, minerals that form in water, and layered rocks that record a wetter past. Mars today is cold and dry at the surface, but the evidence suggests that long ago it had environments where liquid water existed. The Moon, too, is not perfectly dry. Missions including LCROSS helped confirm water ice in permanently shadowed craters near the lunar poles. These regions are so cold and dark that ice can survive for long spans of time. Pluto changed from a distant point of light into a world when New Horizons flew past it in 2015. Instead of a dead, simple dwarf planet, Pluto showed mountains of water ice, nitrogen glaciers, smooth plains, and complex geology. Even at the edge of the solar system, small worlds can be active and intricate. The discovery of the Kuiper Belt made Pluto's neighborhood clearer. Beyond Neptune lies a broad region of icy bodies, remnants from the early solar system. Pluto is not alone there. It is part of a population, one member of a distant family of frozen worlds. Eris, another large Kuiper Belt object, helped force the planet definition debate that led to Pluto's reclassification as a dwarf planet. That story is not only about names, it is about how discovery can reshape categories. The solar system did not change, but our map of it did. The giant planets also became stranger with close observation. Voyager revealed that ring systems are not unique to Saturn. Jupiter, Uranus, and Neptune have rings too, fainter and darker, like quiet signatures of debris, moons, and gravity. Saturn's moons opened some of the deepest astrobiological questions in the solar system. Enceladus, small and icy, sends geysers of water vapor from its south polar region. Cassini flew through those plumes and found evidence of a subsurface ocean. A moon that looks frozen from outside may hold liquid water beneath its crust. Titan, Saturn's largest moon, has lakes and rivers of liquid methane and ethane on its surface. It is the only world besides Earth known to have stable surface liquid today, though the liquid is not water. Titan's orange haze, cold chemistry, and hydrocarbon weather make it a kind of alternate world, familiar in shape and alien in substance. Beyond the planets, the solar system has received visitors. In 2017, astronomers detected Oumuamua, the first confirmed interstellar object passing through our solar system. It moved on a path that showed it came from outside the Sun's family of worlds. Its shape, brightness changes, and slight non-gravitational acceleration produced debate. The simplest lesson is not that Oumuamua was one thing with certainty. The lesson is that the solar system is not sealed. Objects from other stars can pass through it. Some may be rocky, some icy, some altered by cosmic rays during long journeys between stars. Comet Borisov, discovered in 2019, became another confirmed interstellar visitor. Unlike Oumuamua, Borisov looked more clearly comet-like, with gas and dust around it. Together, these visitors suggest that material from other planetary systems occasionally crosses our neighborhood. Now the view widens beyond the solar system into the hidden architecture of galaxies. In the 20th century, astronomers studying galaxy rotation found something strange. Stars in the outer regions of many galaxies move too quickly to be explained by visible matter alone. If only stars, gas, and dust were present, the outer stars should have orbited more slowly. Vera Rubin's measurements made the problem impossible to ignore. Galaxies behaved as if they were embedded in far more mass than we could see. This unseen mass became known as dark matter. Dark matter does not seem to emit, absorb, or reflect light. It reveals itself through gravity. It helps explain galaxy rotation, gravitational lensing, galaxy cluster behavior, and the growth of large-scale structure. The bullet cluster became one of the clearest visual arguments for dark matter. In that collision of galaxy clusters, hot, ordinary gas slowed and lagged behind, while most of the gravitating mass, mapped by lensing, appeared offset from the gas. The usual interpretation is that dark matter passed through the collision with little interaction. Even here, science remains alive. Modified gravity theories, including Moand-like approaches, continue to be tested against observations, and recent analyses still examine whether some cluster evidence can be explained differently. But the broad standard picture remains that dark matter is a real component of the universe, known by gravity, though not yet identified as a particle. Dark matter leads naturally to the cosmic web. Galaxies are not scattered randomly. Surveys reveal filaments, sheets, clusters, and voids. Dense regions connect like threads. Vast underdense regions open between them. The universe has a large-scale structure shaped by gravity from tiny early differences. Imagine a map of cities seen from far above at night, with bright knots and long roads between them. The cosmic web is not flat like a road map, and it was not designed, but the image helps. Galaxy clusters gather at the knots. Filaments stretch between them. Voids are quieter regions where fewer galaxies live. The great attractor belongs to this larger gravitational landscape. Our local group, including the Milky Way and Andromeda, is moving with other galaxies toward a massive concentration of matter hidden partly behind the plane of our own galaxy. The name sounds dramatic, but the idea is simple. Gravity from enormous structures shapes the motion of galaxies across space. Andromeda gives that motion a personal anchor. The Milky Way and Andromeda are moving toward one another and are expected to merge in several billion years. The stars themselves will almost never collide because the distances between stars are vast. But gravity will reshape both galaxies, pulling streams, changing orbits, and eventually forming a new combined system. Inside many galaxies, another discovery waits at the center. Astronomers have found that nearly every large galaxy appears to host a supermassive black hole in its core. The Milky Way has Sagittarius A star. Other galaxies hold black holes millions or billions of times the mass of the Sun. Their masses seem linked in some way to the galaxies around them, suggesting that galaxies and central black holes grow together across cosmic time. Quasars show the bright side of this story. A quasar is powered by a supermassive black hole feeding on surrounding material. The black hole itself is dark, but the gas falling toward it can become intensely luminous. Astronomers keep finding quasars from when the universe was very young, showing that some supermassive black holes grew astonishingly fast. That early growth is one of the puzzles James Webb is helping sharpen. The James Webb Space Telescope looks in infrared light, ideal for studying very distant galaxies whose light has been stretched by cosmic expansion. Its deep field images revealed thousands of galaxies in small patches of sky, including some from the early universe. Some early Webb galaxies seemed at first surprisingly massive and mature for their age. They raised questions about how quickly galaxies could assemble after the Big Bang. Since then, astronomers have worked to refine distances, masses, star formation histories, dust effects, and model assumptions. The tension has become more nuanced. Webb is not simply breaking cosmology, but it is forcing galaxy formation models to become more careful. This is a beautiful kind of discovery. A telescope does not only confirm what scientists hope to see, it improves the question. It shows where models were too simple, where measurements were uncertain, and where the early universe was more active than expected. Other candidate discoveries need even more patience. Astronomers have found possible signs of exomoons, moons orbiting planets around other stars, but no exomoon has been confirmed. Candidates such as possible moons around distant giant planets remain difficult because the signals are tiny and indirect. The discovery would be important because moons may be common places for oceans, volcanoes, atmospheres, and complex environments. Venus offered another cautionary lesson. A tentative detection of phosphine in Venus's clouds was announced in 2020, raising discussion about unusual chemistry and even the possibility of microbial life. Follow-up studies disputed or complicated the claim. The careful version is that Venus remains scientifically interesting, but phosphine is not a simple proof of life. The Gliese 581 system gave an earlier lesson in habitable zone excitement. Some claimed planets in that system might be potentially Earth-like, but later analyses questioned or withdrew some of those claims. Even when a candidate fades, it can change the field by sharpening methods and teaching astronomers how easily faint signals can mislead. This is part of the calm honesty of science. A retracted claim is not only a failure, it can be a correction that leaves the field stronger. The search for life's ingredients continues closer to home as well. Curiosity found organic molecules preserved in Martian rocks, along with seasonal methane variations that remain scientifically interesting. Organic molecules do not mean life by themselves. They are carbon-based chemistry, and they can form through non-biological processes. But they show that Mars has preserved some of the ingredients and clues scientists need to study its past. Solar neutrinos gave another kind of clue from our own star. For decades, detectors measured fewer neutrinos from the Sun than theory predicted. The solution was not that the Sun was badly misunderstood, but that neutrinos change flavor as they travel. The Sudbury Neutrino Observatory helped confirm this, solving the solar neutrino problem and showing that neutrinos have mass. This is a quiet discovery with a deep consequence. The Sun sends particles through space and through Earth, almost all passing unnoticed. By counting them carefully, scientists learned something about both the Sun and the fundamental behavior of matter. Inflation belongs to the earliest moment of the story. It is the idea that the universe underwent an extremely rapid expansion in a tiny fraction of its first second. Inflation helps explain why the universe looks so smooth on large scales and why tiny early fluctuations could seed later structure. Measurements of the cosmic microwave background by COBE, WMAP, and Planck support a picture with tiny temperature variations across an otherwise very uniform early universe. These measurements do not answer every question about inflation, but they give cosmology a precise map of the early pattern from which galaxies grew. There have also been false alarms. In 2014, the BICEP-2 experiment announced what looked like a possible detection of primordial gravitational waves from inflation. Later analysis showed that dust in our own galaxy could explain the signal. The claim was withdrawn as a detection of primordial waves. That correction is worth keeping in the story. The universe is subtle. Dust can mimic a signal from the beginning of time. Careful science must separate the near from the far, the foreground from the deep past, the beautiful possibility from the confirmed result. Even galaxies themselves can challenge assumptions. Some ultra-diffuse galaxies appear to have unexpectedly little dark matter, though individual cases remain debated and difficult. These faint, spread-out galaxies remind astronomers that galaxy formation is not one simple recipe. Direct imaging of exoplanets gives another kind of wonder. Most exoplanets are found indirectly, through transits, wobbles, or microlensing. But in some systems, telescopes have captured actual images of planets orbiting other stars. These are usually young, massive worlds far from their stars, glowing in infrared light. They are not easy targets, but they make the idea of other worlds feel immediate. The first detections of exoplanet atmospheres did something similar. When a planet passes in front of its star, a small fraction of starlight filters through the planet's atmosphere. That light can carry chemical fingerprints. Hubble detected sodium in the atmosphere of HD 209458b, showing that astronomers could study the chemistry of worlds light years away. Now, telescopes can ask increasingly delicate questions. Is there water vapor? Is there carbon dioxide? Are there clouds or hazes? Is a planet losing its atmosphere? No single measurement answers everything, but each spectrum turns a distant point into a physical world. The universe's age is another discovery made through precision. Measurements from the Planck mission, using the cosmic microwave background, helped refine the age of the universe to about 13.8 billion years. That number is not just a label, it is a scale for everything: stars, galaxies, planets, chemistry, and life. When we look at a galaxy 10 billion light-years away, we are seeing a universe much younger than the one around us now. When we look at the cosmic microwave background, we see a pattern from before galaxies existed. Every distance in astronomy is also a time. Voyager gives that idea a human-made scale. Voyager 1 and Voyager 2 left Earth in the 1970s and eventually crossed beyond the heliosphere, the bubble of solar influence around the Sun. They became the first human-made objects to enter interstellar space. Their signals are faint now, but they still carry data from beyond the main boundary of the solar wind. The Voyagers are slow compared with light. Light from the Sun reaches Earth in about 8 minutes. Voyager's journey to interstellar space took decades. That contrast gives the mind a useful measure. Space is not only large, it is large in ways that make even our fastest machines feel patient. Before the journey gathers itself into a closing view, there is room to move more slowly through the chain that connects these discoveries. Begin again with the cosmic microwave background, because old light is not only a relic, it is a measuring instrument. When COBE, WMAP, and Planck mapped the faint temperature differences in that radiation, they were measuring variations so small that they can feel almost imaginary. Yet those tiny differences became the guidebook for the whole large-scale universe. One region was very slightly denser, another was very slightly thinner. Over ordinary human time, such differences would mean almost nothing. Over cosmic time, gravity notices. Gravity works patiently. A slightly denser region pulls in more matter. The pull becomes stronger. More material gathers. Eventually, after hundreds of millions of years, the universe begins to grow stars and galaxies along the pattern that was once only a delicate unevenness in ancient light. This is one of the softest ways to understand cosmic structure. The universe did not begin as finished galaxies. It began with conditions. The cosmic microwave background shows those conditions after the universe became transparent. The cosmic web shows what those conditions became after gravity had billions of years to do its work. The discovery of inflation deepens this first chapter. Inflation is not a directly photographed event. It is a theoretical idea supported by several features of the universe, especially its large-scale smoothness and the pattern of early fluctuations. It suggests that in an extremely early fraction of a second, the universe expanded with almost unimaginable speed. The numbers are too small and too large for ordinary thought. A fraction of a second becomes enough time for space to change dramatically. Quantum scale variations may become the seeds of galaxy scale structure. A tiny beginning becomes an enormous pattern. For sleep narration, the useful image is not an explosion, but a cloth of possibility being stretched so quickly that minute wrinkles become the first hints of future cosmic geography. That image has limits because the universe is not literally a cloth floating inside a larger room, but it helps the mind rest with the idea that the grandest structures can begin from something subtle. The cosmic web, the clusters, the voids, the Milky Way, and Earth itself belong to a story where small differences preserved in old light became places. Expansion also deserves a slower breath. When people first hear that distant galaxies recede faster when they are farther away, it can sound as if Earth sits at the center of a grand retreat. But the standard picture does not put us at a special center. Any observer in a sufficiently distant galaxy would see other unbound galaxies receding in a similar large-scale pattern. A simple analogy is raisin bread rising in an oven. Each raisin sees the other raisins moving away as the dough expands. No raisin needs to be the center of the loaf. The analogy is imperfect because bread expands into an oven and the universe does not require that kind of outside. Still, it helps separate expansion from an ordinary explosion. Redshift is the evidence written into light. As light travels through expanding space, its wavelength can stretch. A galaxy's spectrum becomes a record of the journey. Lines that should appear at one wavelength appear shifted toward longer wavelengths. From that shift, astronomers infer distance, motion, and cosmic history. This is why a telescope is also a time instrument. It gathers light, but the light arrives late. The moon arrives a little more than a second late. The sun arrives about 8 minutes late. Andromeda arrives about 2.5 million years late. Deep galaxies arrive from epochs before the sun existed. The James Webb Space Telescope takes advantage of this old light principle in a special way. Distant galaxy light has been stretched into infrared wavelengths by the expansion of the universe. Webb was designed to see that stretched light. It looks for galaxies not only far away, but far back. When Webb finds unexpectedly bright early galaxies, the question is not simply, is cosmology wrong? The better question is, what exactly are we seeing? Are the stellar masses overestimated? Is dust changing the color? Are brief bursts of star formation making a galaxy look more mature than it is? Is a growing black hole adding light? Are we seeing rare systems, or a population that models did not fully anticipate? That is why Webb's early galaxy discoveries are so valuable. They do not have to overthrow the universe to matter. They sharpen the timeline. They show that the first galaxies, black holes, stars, and chemical enrichment may have developed quickly and unevenly. The early universe was not a quiet waiting room. It was already becoming structured, luminous, and complicated. The same care belongs to distant quasars. A quasar from the first billion years of cosmic history is not merely a bright point. It is evidence that a supermassive black hole had already grown large enough to power an enormous beacon. That raises a question. Did the first black holes begin as remnants of massive stars, or as direct collapses of gas, or through some other pathway? How did they feed so quickly without blowing away the very material they needed to grow? Here, the sleep-friendly image is a lantern in a young city. The universe is still early, still assembling its first neighborhoods, and yet a central fire is already bright enough to be seen across billions of years. The quasar is not calm in itself. Its environment is extreme. But by the time its light reaches Earth, the violence has been transformed into information. Black holes make another bridge between discovery and method. The first black hole image did not come from one ordinary telescope taking one ordinary picture. The Event Horizon Telescope connected observatories around the world, using Earth itself as part of the instrument. By combining signals from many locations, astronomers created the resolution needed to study the region close to a supermassive black hole. This is a beautiful detail because it turns the planet into a quiet measuring device. Radio dishes separated by continents watch the same distant object. Atomic clocks keep time. Computers combine the data. From the surface of Earth, human beings assemble a virtual telescope wide enough to see the shadow of gravity around a black hole. Sagittarius. A star adds a more intimate scale. It sits at the center of the Milky Way, hidden from visible light by gas and dust in the galactic plane. Infrared and radio observations can reach through that obscuring material. For years, astronomers watched stars near the galactic center swing around an unseen mass. Those stellar orbits showed that millions of solar masses were packed into a very small region. So the image of Sagittarius, a star, did not arrive alone. It rested on decades of evidence: stellar motion, infrared observation, radio astronomy, theory, and careful patience. The photograph-like ring was a new chapter, but the discovery had been forming for a long time. Gravitational waves also ask for patience. The first LIGO detection lasted only a fraction of a second in the data, but the system that produced it had evolved over immense time. Two black holes orbited one another, losing energy as gravitational waves, drawing closer, moving faster, and finally merging. The last moments created the strongest signal, but the entire story was written by gravity long before the detector heard it. The detection itself is almost impossibly delicate. Laser beams travel down long arms. Mirrors hang isolated from vibration. A passing gravitational wave stretches one arm and squeezes another by a tiny amount. The change is so small that everyday language can barely hold it. Yet that small change carries news from a cosmic merger. There is a peaceful paradox here. Some of the universe's most violent events arrive as the gentlest measurements. A black hole collision becomes a faint wiggle in an instrument. A neutron-star merger becomes a short signal and a fading glow. A gamma ray burst becomes a timestamp, a direction, a spectrum, and a follow-up campaign. Multi-messenger astronomy is powerful because no one messenger tells the whole story. Gravitational waves reveal the motion of dense masses. Light reveals hot matter, ejecta, afterglows, and chemistry. Neutrinos can escape from places light struggles to leave. Cosmic rays carry another kind of energetic clue, though their paths are bent by magnetic fields. The universe is therefore not one book, but many translations of the same event. Each messenger preserves something different. Put together, they turn a distant collision into a physical story. The exoplanet chapter deserves the same slower treatment. 51 Pegasi b was surprising because it was a hot Jupiter, a giant planet extremely close to its star. Before such discoveries, many people expected other solar systems to look more like ours, with small rocky worlds close in and giant planets farther out. The first major discoveries showed that nature was less tidy. Giant planets could migrate, planetary systems could rearrange. The solar system was not the only template. Kepler then changed the statistics. A planet crossing its star blocks only a tiny fraction of light. But if a telescope watches long enough and precisely enough, that tiny dip becomes evidence. If the dip repeats, it gives an orbital period. If the star is understood, the depth of the dip gives the planet's size. Follow-up measurements can estimate mass. Together, size and mass can suggest whether a planet is rocky, gaseous, or somewhere in between. This is a very gentle method at heart. The planet is not seen directly. It is known by the missing light it creates. A world announces itself by making its star slightly dimmer for a little while. Atmospheres take the method further. When a planet transits, a little starlight passes through the thin edge of its atmosphere. Molecules in that atmosphere absorb certain wavelengths. The result is a faint chemical fingerprint. Sodium around a hot giant planet was an early proof that atmospheres beyond the solar system could be studied. Today, astronomers try to read water vapor, carbon dioxide, methane, clouds, hazes, and atmospheric escape in distant worlds. This kind of discovery is humbling. A planet may be dozens, hundreds, or thousands of light years away, yet a small change in starlight can reveal something about its air. Direct imaging is different. It is difficult because stars are bright and planets are faint. Seeing a planet near its star is like trying to see a firefly beside a searchlight from very far away. The planets that can be imaged are often young, hot, massive, and far from their stars, glowing in infrared light. But when direct imaging works, the idea of another world becomes less abstract. There in the data is the planet's own light. Habitable zone worlds should be handled with care. The habitable zone is not a garden fence. It is a range of distances where liquid water could exist on a planet's surface if other conditions cooperate. Atmosphere matters. Pressure matters. Clouds matter. Volcanism, rotation, tides, stellar flares, and planetary history all matter. TRAPPIST. 1 is compelling partly because it is compact. 7 Earth-sized worlds orbit close to a small red star. From the surface of one, if it had a surface and a clear sky, neighboring planets might appear larger than our moon appears from Earth. The system gives the imagination a calm, close architecture, worlds moving in tight rhythm around a dim star. But small red stars can be active. Flares and radiation may erode atmospheres. Tidal locking may create permanent day and night sides. None of this rules out habitability by itself, but it makes the question richer than a simple yes or no. Proxima Centauri b carries that same richness. It is the nearest known exoplanet in the broad, temperate conversation, but nearest does not mean near in human terms. A light signal takes more than 4 years to arrive. A spacecraft like Voyager would need tens of thousands of years to cross such a distance. Even the closest possible worlds around other stars belong to deep time. The solar system's ocean world discoveries help make distant habitability more imaginative. Enceladus is a small moon, yet it has a global ocean beneath ice and vents material into space. Europa, though not highlighted in the original source list, belongs to the same family of questions. Icy surfaces, hidden oceans, tidal heating, and chemistry beneath the crust. These worlds show that liquid water does not require a sunny beach. It can exist under ice, warmed by gravity's kneading. Titan shows that liquids and weather can be alien. On Earth, water rains, flows, evaporates, and returns. On Titan, methane and ethane can play a similar surface role in freezing conditions. Lakes and rivers exist, but the chemistry is not Earth's chemistry. It is a reminder that a familiar shape in nature can be built from unfamiliar ingredients. Mars, meanwhile, is the lesson of a changed world. Ancient riverbeds and lake deposits tell us that Mars was once wetter. Today, the surface is cold, dry, and exposed to radiation. Its atmosphere is thin. Its global magnetic shield is gone. The question is not only whether Mars ever had life, but how a planet can move from possibility to loss. Venus offers another planetary warning from the opposite direction. It is similar to Earth in size, yet its surface is hot enough to melt lead under a crushing atmosphere rich in carbon dioxide. The disputed phosphine claim belongs inside this caution. Venus may hold chemical surprises in its clouds, but chemistry is not the same as biology. A strange molecule is an invitation to study, not a conclusion. When these planetary stories are placed together, the search for life becomes more careful and more beautiful. Life is not found by hope alone. It requires context. Water, carbon chemistry, energy, stability, atmosphere, and time all interact. A single clue can be meaningful, but a biosignature is stronger when many clues point together. Dark matter also becomes clearer when slowed down. Galaxy rotation curves are often described with a graph, but the physical image is simple. In the solar system, planets farther from the Sun generally orbit more slowly. If visible matter were the whole story in a galaxy, outer stars might be expected to show a similar decline. Instead, many outer stars move as if more mass surrounds the galaxy than visible stars and gas provide. That missing mass is not a small correction. In the standard picture, galaxies sit inside extended dark matter halos. The luminous disk is only the bright part. The halo is larger, darker, and known through gravity. Gravitational lensing gives a second image. Mass curves spacetime, and curved spacetime bends the path of light. A galaxy cluster can magnify and distort galaxies behind it, creating arcs, streaks, and multiple images. By measuring those distortions, astronomers map mass, including mass that does not shine. The bullet cluster combines lensing with collision. Hot gas, which is ordinary matter, interacts and slows. The lensing mass appears offset. In the standard interpretation, dark matter moved through more freely, separating from much of the ordinary gas. This remains one of the strongest pieces of evidence for dark matter, even while modified gravity alternatives continue to be studied. That tension is useful for the listener. because it shows how science breathes. Evidence can be strong and still examined. A leading model can succeed broadly and still have unknowns. Dark matter is strongly supported as an evidence pattern, but the particle nature of dark matter remains unknown. Direct detection experiments have searched for dark matter particles for decades. Underground detectors are placed deep below Earth's surface to reduce ordinary background noise. They wait for rare interactions that might reveal a dark matter particle passing through. So far, no confirmed detection has arrived. This does not erase the gravitational evidence. It narrows possibilities and pressures favored models. Dark energy is different again. Dark matter helps structures gather. Dark energy is connected to accelerated expansion. One is inferred from extra gravitational attraction in galaxies and clusters. The other is inferred from the expansion history of the universe. Their names are similar because both are not seen directly through light, but they are not the same mystery. The cosmic web is the landscape where these mysteries meet. Dark matter helps create the gravitational scaffolding. Ordinary matter falls into that scaffolding, cools, forms stars, and lights up galaxies. Dark energy shapes the large-scale expansion that changes the future distances between unbound structures. A galaxy cluster is like a weather system of gravity. It contains many galaxies, hot gas between them, dark matter around and through them, and light from background galaxies bent by the cluster's mass. A void is not nothing, but an underdense region where fewer galaxies formed. A filament is a long structure where matter gathered more strongly. The Great Attractor and related large-scale flows remind us that the Milky Way is not at rest. Earth orbits the Sun. The Sun orbits within the Milky Way. The Milky Way moves within the local group. The local group moves within larger flows of galaxies. Stillness is a local feeling, not a cosmic fact. The Milky Way and Andromeda merger gives a future version of that motion. Several billion years from now, the two spiral galaxies will pass through and around each other. Stars are so widely separated that direct stellar collisions will be rare. Gas clouds will interact more strongly. Star formation may be triggered. Tidal tails may stretch outward. Over time, the two galaxies may settle into a larger remnant. The discovery here is not only that a merger will happen, it is that galaxies have lives. They grow by eating smaller galaxies, pulling streams of stars into halos, collecting gas, forming stars, and changing shape. The Milky Way is not a finished object. It is a history still moving. Pluto and the Kuiper Belt offer the same lesson on a smaller scale. Before the Kuiper Belt was understood, Pluto seemed lonely. After the discovery of many icy bodies beyond Neptune, Pluto became part of a population. The emotional change is interesting. A world can lose a category called planet and gain a deeper context as part of a distant icy frontier. Eris made the problem impossible to ignore because it was comparable to Pluto in significance. If Pluto was a planet, should Eris be one too? What about other large icy bodies? The solution was controversial, but scientifically it reflected a real expansion in knowledge. Categories had to respond to discoveries. Oumuamua and Borisov extend that frontier beyond the Sun. They are not just strange passing bodies. They are samples of the fact that planetary systems exchange material with the galaxy. During planet formation, gravitational encounters can eject comets, rocks, and icy bodies into interstellar space. Some travel for ages before crossing another system. Imagine the solar system as a harbor in a dark sea. Most objects belong to the harbor. Planets, asteroids, comets, moons, dust, and spacecraft follow paths tied to the Sun. But occasionally, something from another harbor passes through. It does not stay. It carries no label. Its path is the clue. That quiet passing helps connect local astronomy to galactic astronomy. The Sun is one star among hundreds of billions in the Milky Way. If other stars form planets, eject small bodies, and send material into interstellar space, then the galaxy may be filled with wandering fragments of planetary systems. Rogue planets are larger wanderers. Some may have formed around stars and been thrown out. Others may form in isolation, though that question is still studied. A rogue planet without a star would not have daylight, but it might have internal heat. If it had a thick atmosphere or a subsurface ocean, it could remain geologically or chemically interesting in the dark. This is not a claim of life. It is a widening of imagination. A world does not need to look like Earth to be a world. It may orbit a star, drift alone, hide an ocean, carry methane weather, or glow faintly in infrared after formation. The last discoveries are really about humility. The bicep. Two correction teaches humility in measurement. Galactic dust can imitate a signal from the early universe. The Venus-phosphine debate teaches humility in chemistry. A possible molecule is not a life detection. Exomoon candidates teach humility in faint signals. A dip, a timing variation, or a cloud of sodium may be suggestive without being final. Ultra-diffuse galaxies with unusual dark matter content teach humility in categories. If some galaxies appear to lack the expected dark matter, astronomers must ask whether the measurements are right, whether the formation history is unusual, or whether the model needs refinement in special environments. JWST, early galaxies, teach humility in interpretation. Brightness is not mass by itself. Color is not age by itself. A point of infrared light may contain stars, dust, a black hole, or a blend of effects. The early universe is not simple just because it is early. This humility is not discouraging. It is part of the wonder. Science does not become weaker when it corrects itself. It becomes more trustworthy. A claim is tested. A foreground is subtracted. A model is revised. A telescope observes again. An instrument improves. A new survey adds statistics. The universe remains patient while the map becomes clearer. So, the 50 discoveries become one journey. The cosmic microwave background tells us the universe has an early thermal history. Expansion tells us space changes with time. Dark energy tells us expansion is accelerating. Black holes tell us gravity can create regions where light cannot escape. Gravitational waves tell us space-time can ring. Neutron-star mergers tell us heavy elements can be forged in collisions. Exoplanets tell us worlds are common. Icy moons tell us oceans can hide under frozen crusts. Dark matter tells us gravity is revealing something unseen. Webb tells us the early universe is richer than expected. And the disputed discoveries matter too. Exomoons, phosphine on Venus, unusual galaxies, early massive candidates, distant quasars, dark matter alternatives, and interstellar visitors all show that the map is still being drawn. That is the calm center of cosmic discovery. The universe is not a solved machine, it is a readable mystery. A discovery begins as a signal. A signal becomes a pattern becomes a question becomes an instrument, a model, a debate, a correction, and sometimes slowly a new piece of reality. The night sky above Earth can look still, but it is full of motion. The moon carries ice in shadowed craters. Mars holds dry riverbeds and buried clues. Saturn's moons carry methane lakes and water plumes. The Kuiper Belt circles beyond Neptune. Interstellar objects pass through. The Milky Way turns inside a dark matter halo. Andromeda approaches. Farther away, galaxies trace the cosmic web. Quasars burn in the early universe, and ancient light still surrounds us from every direction. Nothing here needs to be hurried. The cosmic microwave background has waited for billions of years. The light from Andromeda has traveled for millions of years. The stars make elements slowly, spend their fuel slowly, and scatter their material into space. Even the most explosive events become, after crossing distance, a quiet measurement in a detector on Earth. So let the story settle into scale. We live on a planet with oceans and weather, circling an ordinary star inside a galaxy among many galaxies. We are made of atoms shaped by stars, chemistry, time, and gravity. We are small but not separate. The same laws that bend light around a cluster also hold Earth near the Sun. The same universe that made black holes also made carbon, water, and thought. The discoveries do not make the cosmos smaller, they make it more intimate. They show that the universe can be known by traces, a hiss of microwaves, a dimming star, a pulse of radio light, a ring around a black hole, a tiny stretch in a laser arm, a curved galaxy image, a molecule in a Martian rock, a plume from an icy moon. Each trace is faint. Each trace is enough. And as Earth turns quietly beneath the stars, the old light continues to arrive. The galaxies continue their slow motion. The cosmic web holds its bright threads and dark spaces. The questions remain open, not harshly but gently, like distant lamps still visible across the night. Good night.